If you would recall, last time on Calculus 1, we started talking about area under the curve. We want to be able to calculate area under the curve. And all we know about area is that area is equal to length times width. You have all kinds of niche formulas for area, for triangles, for circles, but now we've got some continuously variable length. So we're just going to pull this back to basic principles. Area is equal to length times width. We're just going to look at a low resolution version of what's going on. We're going to use the discrete to model the continuous. Calculus is about continuous change. And the way we do that is we make a discrete change to model the continuous change. And we just do this discrete change more often. How often? Forever. This is your life now. So the area is length times width. The thinking is that the length is continuously variable. So I don't just get to multiply two constants. Bummer. So what we're going to do is make the length constant for small bits of the width. Very technical term, bits of the width. Small subintervals along the width. And we're going to call that width delta x. They don't actually need to be all the same, but we're going to make them all the same because why would we want to make our lives that much more difficult? So small pieces of the width delta x. Then we're going to, for each of those bits of the width, we're going to make the function constant and evaluate the function somewhere on that little bit and say that is the height of the function for this whole little bit. Once we have that height, the value of the function, we have the width delta x, we can multiply those two to find the area. This was our goal. Stupid length is all continuously variable. Nah, forget that and make it constant for this little piece so we can multiply. Then all of our terms are going to be different, so we just have to add them up. This is still just a discrete model of our continuous situation because I have all these little bits, but they're still little bits. So we're going to think about what do we do when we want to add up all the areas, but there's an infinite number of them and there's no place to put the plus sign. So that's where we're at right now. Well, let's look at all the stuff. This is all the thinking that we went through last week. I had to limit this to 6 steps because I only have 6 different colors of pen aside from our, like the basic black pen. So I guess technically I have a dark blue pen put on the screen, and also in the scans, the dark blue pen is kind of indistinguishable from the black. So only I can see the difference on the original, and so I can't use it because I know it's not showing up and it bugs me. So here is the thinking that goes behind it. Now we want to be able to encode all of this stuff. So the way that looks is what we're doing is just length times width. And so we're breaking our interval because we want under a curve and above an interval. So we're going to break the interval up into a bunch of little pieces delta x, and we're going to evaluate the function. So at each point I have an area is length f evaluated at some xi. That's the indication right there that we are working with a discrete model because I have indexed my x values. Here's x1, x2, x3, x4, all the way up to x sub n. I've got an indexed set. An indexed set is going to be a discrete set because we can number them all. There's my length. I'm going to multiply it by width. And that's the area of one rectangle. That's an area of just one rectangle. What we want to do is add up all of these rectangles. And they're just numbered. First, second, third, fourth. So I'm going to add up all the rectangles. Area 1, area 2, area 3, all the way up to area n. The way we do that is we say, I'm going to make a sum. I'm going to use summation notation, and this might be new. I'm going to make a sum as I goes from 1 to n. That capital sigma is a symbol for a sum. The sum is I goes from 1 to n of f at xi times delta x. So this is summation notation. We use a capital, oops, scroll. We use a capital sigma for summation notation. The capital sigma is for a summation. Replace the I with a 1, then a 2, then a 3, then a 4, and then just add them all up. Now we add up all the areas of the rectangles. Now we apply calculus. Calculus says do that forever. Finally, we use an infinite number of rectangles. This is the calculus way. Whatever you do to make your approximation better, do that forever. So finally, we do the limits as n goes to infinity. So here we are using an infinite number of rectangles. What we're looking at here, we refer to as a Riemann sum. This is a Riemann sum. So the I equals 1 part is how the summation notation works. So let's take a look at this capital sigma summation style stuff. It took me all of 1 sigma written properly before I started using my lazy sigma, which is a backwards 3. That's like the shortest I could possibly go. Sometimes I write 3 or 4 like properly angular capital sigmas with a little serif on them, but now it was 1. You got 1 capital sigma, so I hope you were watching. So when we have an expression, we have an indexed expression with an I in it. So like the sum as I goes from 1 to n of say I squared would be, well, actually let's, instead of using n, n is fine. I'm going to do 1 squared plus 2 squared plus 3 squared plus 4 squared, and then just keep going until whatever number here is on top, n squared. So that's how a summation notation works. So the sigma says add up all the things when I goes from 1 to n. It's a discrete sum. Just looking into the future. It's possible that we go from, say, from 0, we could start from, wherever we want, wherever it happens to be convenient for us. So in the previous one, I said from 1 to n, so I have n terms. It makes, when we have a finite count, it's helpful to be able to know the number of terms. But in this one down here, I've got 3 times 10 to the negative I, as I goes from 0 to infinity. So they're showing that we could start wherever we want. It doesn't have, we don't have to start counting at 1. It's also going to be acceptable in future to just put in infinity when instead of writing limit as n goes to infinity. Mainly because we mean a different thing. Any questions? What's cool is sometimes we, even though we have an infinite number of terms, sometimes we still get to know what the sum is. So that's how that capital sigma, that sigma notation works. We use a capital sigma for a summation. It just means put all those values of the index. Here's a range of index values. Start at 1 and go up to n. And then I'm writing limit as n goes to infinity. This is what happens when we use an infinite number of rectangles. This produces what we call a Riemann sum. How's everybody okay? This is the thinking behind finding the area under a curve and above an interval. I haven't justified why we would even want to do such a crazy thing. I just told you at the beginning of class, like, oh, this is one of the things that we're going to do. Slope of the tangent line, area under a curve. And everybody's like, oh, all right, why are we going to do that? I'm like, oh, quiet you. And then I just moved on. And here we are. So if you're worried about when this might come up, this is all based on multiplication. Anywhere you're going to use multiplication, and one of those factors might end up being continuously variable, that's when we're going to need to know area under a curve. Distance is equal to rate times time. Your rate can be continuously variable. Whenever you're moving around in the physical world, your rate is continuously variable. You don't go from 0 to 60 without passing through every real number valued speed from 0 to 60. You don't get to skip like 50 miles per hour. At some point, if you're going 60 and you started from rest, at some point you were going 50. Because we all change our speed by a continuous function. Wasn't always this way. We used to be able to change our speed discontinuously, but driving was just awful. So we're like, all right, that's it. No more of this instant acceleration business. Continuous for everybody. We're like, oh. But then drag races happened. We're like, oh, all right, now this is okay. This is okay. Because there weren't, before it wasn't drag races. We could all just accelerate infinitely. So it'd be like, I'll go, and then we were done, like right away. It's just whoever went at the right time, they won. You know what I mean? It's like Jeopardy. You know the trick to Jeopardy? You buzz in. That's it. Be the first to buzz in. And then take the time. Don't decide you know the answer, then buzz in. You'll always lose. Always lose. Just buzz in. Assume that you know the answer. That's what you have to do. Why did the computer win at Jeopardy? Because it buzzed in faster than anybody else could. That's it. If you want to make the Jeopardy fair, you don't let the computer buzz itself in. You have a human buzz in. You know what I mean? You got to be confident. You can't know and then go. You have to just go and then know the answer. Because you get time after that. You don't have time to buzz in. You buzz in first, and you've got 5 seconds to remember to know what the answer is. So if any of you end up on Jeopardy, just buzz in. All right, what are we talking about? Oh, yes, Riemann sum. So this construction is a Riemann sum. I like this. We never write this down, but this is important because this is how we think about this problem. This is way, though, now we've got to figure out how we're going to calculate this problem. So we have different notation for this. And this is what happens. Our f of x, f at xi, that's discrete, right? Evaluate this function at this specific point, the first point, then the second point, then the third point. That becomes the continuous function f of x. Just like our delta y over delta x in our slope problems for the derivative, became dy over dx for our instantaneous rate of change, our delta x becomes the instantaneous or the very thin dx. Just like before, delta x becomes dx. Limit as n goes to infinity of the sum as I goes from 1 to n, all that gets replaced. That's the machinery for a discrete sum. We ain't got a discrete sum anymore. We have a continuous sum, so we have new notation for it. We put an integral symbol, which is kind of like a stretchy S. So our capital sigma for a discrete sum becomes our continuous S. It's kind of like a stretchy S. Like the holes on a violin. That's why that one calculus book has a picture of a violin on it all the time. But now, instead of an index set, instead of from 1 to n that we're indexing, we just say what x values we're plugging in. So it's going to be from A to B. And this symbol is the definite integral. This is the definite integral of f of x dx from A to B. And these are x values. So here we have the definite integral from A to B of f of x dx. So this symbol is the definite integral of f of x dx from x equals A to x equals B. Here's what we want to notice. We are calculating the same thing. F of x times dx. Same as f at xi, delta x. We're calculating the same thing. F of x length, delta x width. F of x dx. We're calculating the same thing. But instead of doing this over an indexed set of x's, I'm just saying for all the x values from A to B. So this first part up here, we're going to take this expression, f of x dx, then the integral part, the integral from A to B is saying all the x values where you should do this. Evaluate the expression f of x dx at all the x values between A and B. Evaluate the expression f of x dx at all the x values from A to B, at all those x values. Then add up the results. This last statement you should be looking at and being like, oh, that is very suspicious that you're saying add up all the results. This is a continuum where we put the plus signs. To which I respond, quiet, you. That's how we think about it. We're thinking of this as a continuous sum. So this third statement here, very suspicious. Because when we're thinking about a continuum, there is no next number. There is no next real number. The integer that comes after 5 is 6. The integer that came before 5 is 4. But the real number that comes after 5, there isn't one. There isn't a next real number after 5. There isn't even a next rational number after 5. So this is the definite integral from a to b of f of x dx. You could swap two prepositional phrases. You could say the definite integral of f of x dx from a to b. Whichever sounds better to you. Just pick one. That's how to read that symbol. Here's how we think about calculating that symbol. Here's what we think what we're doing. The other part that we need to think about is that this is a continuous version of this Riemann sum. That's a continuous version of the Riemann sum. The Riemann sum is a discrete model for the continuous thing that we're trying to calculate. At this point, if you're thinking, dude, didn't you say all this last week? I'm like, oh yeah, I did. Guess what I'm going to be saying tomorrow? The same stuff, because songs don't get stuck in your head because you heard them one time. Now, this does not tell us how to find this area. This just tells us the thinking that goes behind it. Because, like you said, everybody looked very suspicious at this, then add up the results. Be like, oh, where are we going to put the plus signs? Right? You can do it in that Monty Python way. Well, where are we going to put the plus signs? Quiet, you. You haven't got to that part yet. Oh, I didn't have the moose. That wasn't for me. So remember what we're trying to do. Area is equal to length times width. Stupid area is continuously variable. There's the thinking that goes through the Riemann sum. The Riemann sum becomes the definite integral. That's our continuous sum. Now, how do we calculate this definite integral? I'm glad you asked. No one asked, but in my mind, everybody asks. Well, how do we do that? It's like, I'm glad you asked. Like if there was a writer, like one of the students would be like, well, how are we supposed to do that? And they go, well, I'm glad you asked. Like, I don't have a writer, so none of you walk in here with like a script. So it's really frustrating. You know what I mean? All right, here is the cool part. This is super early to get to this cool part, but I don't want to do this in week 15 where we barely have time to think about it. You're all stressed out about finals and all your other classes, as if you're taking other classes or something like that. Let's just do this now. Let's do this now. Here's how we calculate it. We're going to calculate this by I'm going to invent a new function. I'm going to show you a new function. It's going to be capital F. If you've been using all caps before, you got to knock that shit off. Math is case sensitive. This is a lowercase f. A lowercase f. If you wrote a capital F, you capital F fucked up. Because math is case sensitive. And these different ones. We do this. We just do capital F at B minus capital F at A, where capital F is an antiderivative of little f. This is where stuff gets crazy. That's really cool. Derivative is the thing that we've been working on. Antiderivative is, unsurprisingly, just that process backwards. So what I mean is, that is capital F prime at x is f of x. Capital F is an antiderivative of f. This is what we can, one of the things that we can do to calculate this area that we want. This last piece, from definite integral to antiderivative, evaluated at the endpoints of the interval, is the fundamental theorem of calculus. Riemann sum to definite integral to antiderivative using the fundamental theorem of calculus. What? Yes. Capital F prime prime equals lowercase f prime. That is correct. So the second derivative of f would be the first derivative of, the second derivative of capital F will be the first derivative of little f. Any questions? There's a very cool ancient picture. I think it was an Archimedes picture where he has a circle. He drew a circle and he drew a bunch of rectangles in the circle. And he's like, well, just do this forever. And people are like, oh, look, ancient Greece had calculus. That is not true at all. They could not have had calculus. It's not possible. Calculus is based on like things like algebra and functions. They didn't have algebra and functions. They couldn't have had calculus. The important part, the calculus part, is less about this thinking. They had this idea of just do that forever. And they're like, oh, well, what does that mean? So just do that forever. They had that kind of idea, but they had no way to encode that into a useful form until Newton and Leibniz come along and say, essentially just wave your hands at it. They're like, oh, yeah, it's infinitely small. It's like, well, what do you mean? It's like, well, we'll just keep doing it until, well, how will we know when to stop? You'll just know. And all the engineers are like, oh, got it. And they ran with it, right? And then it worked. So this is the Riemann sum. I like writing the Riemann sum because it helps us remember where this came from. We want to remember what we're trying to do. Area under a curve and above an interval. Here's how we think of it. We make a discrete model where the function, instead of being continuously variable, is constant for little bits of the width. Then we just add all those up and then use an infinite number of rectangles. That becomes our definite integral. The next thing that we need to do is figure out how to take the definite integral, find an antiderivative, so you can use the fundamental theorem of calculus to calculate that area. The fundamental theorem of calculus, or this definite integral, is just how we're going to do length times width when the length is continuously variable. So ultimately, since length times width is just one application of multiplication, this definite integral is going to be how we multiply when one of our factors is continuously variable. I use the word antiderivative. So for those of you following along in the book, you're like, oh, dude, it is way too early to be uttering things like antiderivative. Isn't that a forbidden word at a single digit week of calculus 1? And I'm like, oh, no, yes. But that's fine. It's because I believe in you all. Oh, I just advanced the calendar a day. I'm not allowed to do that anymore. I know it's really early to start doing stuff like this, but like I said before, I believe in you all. I know you all can do this. It is not too early. Everybody is fully capable of doing it. Let's think about what happens when we find this derivative business. So the derivative of x to the n is nx to the n minus 1. Let's analyze very carefully what we did. First, we multiply by the exponent. And second, we subtracted 1 from the exponent. And we did it in this order. Subtract 1 from the exponent. Here we are. First step, multiply by n. Second step, subtract 1 from the exponent. Multiply by the exponents, subtract 1 from the exponent. Antiderivative means do this the other direction. Invert this process going the other way. So let's invert this process. This is going from the derivative, from a function to the derivative. Let's go from the derivative back to the function. Let's invert the process. We're going to do inverse operations in reverse order. So this is the instructions for function to derivative. First, multiply by the exponent. Second, subtract 1 from the exponent. If we want to do the inverse of this operation, we'll do inverse operations in reverse order. So what's the inverse of subtract 1 from the exponent? Add 1 to the exponent. And what's the inverse of multiply by the exponent? Divide by the exponent. And I'm going to specifically state divide by the new exponent. So if we want to find the antiderivative of a function, we'll add 1 to the exponent, then divide by the new exponent. If I don't have an interval from a to b, this is an indefinite integral, and it is a way that I can ask for an antiderivative of the function. So first, I'm going to add 1 to the exponent. Starts off at n, so the exponent is going to be n plus 1 when I add to it. And then I'm going to divide by the new exponent. Sometimes the applause is just perfectly fine. And it always makes me happy. I mean, like, I know it's not for me, but it's so funny. The timing is like 1 over n plus 1, and then the applause. See, there's no trick to it. It's just a simple trick. Find the derivative, but in reverse. That's an antiderivative. Now, it did come up with some weird things because before I always talked about the derivative, the derivative, the derivative, the derivative. I was all on about the derivative. And here, I didn't say the antiderivative. I said an antiderivative. And I wrote it in all caps and I underlined it. And I made it look a little bit goth by underlining it with like some really heavy eyeliner. But that's actually it's more like a N-liner. There's no I. Beside the point. I highlighted that and antiderivative part. So that means I got to explain why I said an antiderivative when I kept talking about the derivative. You know what I mean? I need to explain that right now. Otherwise, calculus is going to be just so confusing. So right now, I better explain why I said an antiderivative and not the antiderivative, lest y'all be confused forever about calculus. It's just going to take forever to fix that. So as long as I explain it right now, I think we'll be fine. I just got to do it right now. So the reason that I switched from the derivative to an antiderivative, remember, we got to do this right now, otherwise we'll be confused forever, is, oh, dang, look at the time. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing. What I mean is you can sort this one out. So sort that one out.